So this is an extra example. It is extra because we're going to look at one of the pipes of this pan flute here. And pan flute pipes are closed at one end and open at the other end. And in this topic, we've mainly focused on standing waves where the two endpoints had the same characteristics. So for the standing wave on a string, we had two fixed endpoints. And for the standing waves in pipes, we had open ends at both ends of the pipe in each example we've looked at. But in this case, one end is closed and the other end is open. And I'd like to show how you could figure that out by drawing pictures. Now, it turns out you could also just Google about pipes that are open at one end and closed at the other end. But it's really neat how in physics we can draw sketches and apply principles and figure things out through analysis. So the sketch I'd like to draw here is I'm going to draw a displacement picture of the standing wave in the air in one of these pipes. Now, air goes freely in and out of the open end, which means I think that's going to correspond to an antinode where the air can move a lot. And then at the other end where the air cannot move through the closed end of the pipe, that's going to correspond to a more node type of spot. It's actually formally incorrect for me to call this a node and antinode because it's really the endpoints, but they're behaving in that way, so I like to think about them that way. Strictly speaking, we're supposed to use nodes and antinodes, and especially when we're counting them, especially in relation to things like harmonic numbers, we're supposed to only look at the ones that are not at the endpoints. But this is a picture I have for the standing wave that I think is the most fundamental. If I wanted to get something higher than this, I would probably have to include a node and maybe an antinode as well before I'd get to the end. So this is like the least amount of, like, you could say, wiggling of the standing wave as I move from one end to the other. And I accidentally drew there as I was gesturing with my pen. So I can use this sketch, though, to answer some questions because the length here, this represents the length L of the pipe. But if I look at this partial standing wave I've drawn here, if I were to continue to sketch that out here, right, how much would I need to do before I'd get to a full wavelength? Well, I'd have to get all the way over to, I don't even know if it might even be off the screen here, because I'd have to go crest all the way to crest. And if you look at this part, it turns out this part should be the same length as from here to the next antinode, and then from that antinode to the next node, which would be about here, and then from there to the end, that is somewhere off my whiteboard here. And so that's the way I'm looking at this visually, to convince myself that this section really corresponds to just 1/4 of a wavelength. In other words, 1/4 of a wavelength is equal to L, and that implies that that wavelength is equal to 4L. And since L is equal to 10 centimeters, this is a 40 centimeter wavelength for that fundamental, which I'm going to convert that to 0.4 meters for calculations. And then since I'm asked for frequency and I'm given speed, it makes sense that I would write the formula lambda F is equal to V, and I'm going to divide both sides by lambda to say that F is equal to V over lambda, and so that becomes 340 meters per second divided by 0.4 meters. I turn to my calculator, and my calculator says that that division is 850, and the meters cancel. It's 1/second, but this is a frequency, so I'm going to write that as a hertz. So 850 hertz. So let's go ahead and check that. That is correct.